how do we deal with that? And that there are forecasters involved in many cases, and their mental state may be a factor in the uncertainty that's represented in the forecasts themselves. And you can see that depending on how you form your forecast environment, these will have different influences, and they interact with each other as well. They don't always combine at some point. The second challenge is integrating forecast sources or uncertainty that span different time domains, right? So we have very short-term forecasts, medium-range forecasts, long-range forecasts, and those need to be seamlessly integrated in some fashion, right? Because we don't really want discontinuities in our probabilistic forecasts. So that's another challenge. The third challenge relates to maintaining continuity over space and time. And so if you look at this figure on the left where you see a watershed, we need to have coherency within the watershed, and sometimes very large areas, so that as we combine forecasts and go downstream, that our forecasts continue to make sense. So they're not independent of each other. There's dependencies across spatial and temporal domains if we want to produce outcomes and forecasts that remain rational and consistent with each other. The fourth challenge involves integrating forecaster skill in the meteorology department, right? And so I think there's, these are old slides, right? But there's still forecasters in many cases in the loop in deciding how much is it going to rain, what the temperature is going to be. In the office that I managed for many years, the forecasters had a big influence on the numerical weather prediction model guidance and being able to make adjustments in the time domains of the next several days that were really important to getting the forecast right. So how do you quantify that? It's a little easier to do that when you are just operating with a numerical weather prediction model or some system that is a lot more predictable or consistent. But in many cases, we do have folks that are involved in forecast, and we need to be able to integrate their knowledge and skill as well. And we have, in most cases, still hydrologists that are in the loop. Andy loves them in the loop. Been trying to get them out of the loop forever. They're still in the loop. And there are time domains where they don't need to be. Maybe in the very, very short term, there's no time to get in the loop. And in the longer time domains, they're a lot more stable and you don't really need to be there. But in that time range between, maybe 12 hours to a day and 3 to 5 days, in many cases, having a forecaster in the loop makes a difference. And at least until we can develop data assimilation and data integration techniques that really represent or can catch some of the model excursions that would discourage consumers from using them in the future. So, occasionally our continental scale models get off the tracks, and you really wouldn't want to leave that out there, because if you leave it out there too often, the people that consume it will stop paying attention to you. So it's a risk. But I have seen, and these are old slides, so there's an opportunity for data assimilation and integration, and we're beginning to see that, particularly with machine learning models. So progress. We need to maintain coherence between deterministic and ensemble or probabilistic forecasts. There's a large sector of hydrologic forecast consumers are really more interested in the deterministic forecast than probabilistic. If we're not consistent, they're gonna be very, very confused. We had a conference here, I believe in 2014 for the whole Weather Service Hydrologic Service Program, all the service hydrologists, the RFCs. And I gave a talk there, probably used some of these slides, about probabilistic forecasts. And I told them, I said, in 10 years, if you issue a deterministic forecast, you're going to get laughed at. I was wrong. It's 10 years later, and people are still hanging on to deterministic forecasts. I'll talk a little bit more about that later. But it is important to retain coherence between those two, which can be very different forecast results. The next is really a pretty significant challenge, particularly for folks that operate in regulated systems where there's a lot of dams and reservoir projects that heavily influence the river flows and the floods. So being able to integrate the effect of those diversions and the reservoir regulation into a probabilistic forecast is really not a small thing. And I think that's a challenge to this community. I haven't seen a whole bunch of work done on that, but I believe it's something that's really important. If you look across the U.S., and you look at all of the places where floods are forecast, they're predominantly regulated locations. They're not, they're not unregulated. So you have to model, you have to have the reservoir regulation in your modeling framework somewhere, and how you integrate the uncertainty of the reservoir operator's decisions into your probabilistic forecast is important. You may not do it at all. It could be you said, well, we'll have the uncertainty in the downstream local, but we're just going to assume that they're going to do exactly what they say that they're going to do, and we're going to go with that. I think that's pretty common, actually, and the way it's done in many cases. But it probably isn't the best way to do that, particularly lead times beyond, right? Because, and this is a difficult one because, I've talked to a lot of reservoir operators, and in the middle of floods, and they don't want to tell you what they're going to do because they're not really sure, right? They're going to wait for the next forecast, and they're really not going to tell you, or they're not in a position to say what they're going to do more than a day from now. So this is important, and I think it's a challenge for our community as well. The next challenge is really to address conditional uncertainty. We're pretty good at describing meteorological uncertainty across a whole range of atmospheric conditions, for example, but being able to do that specific for different storm types is also maybe, it's really, really important because there can be significant differences in how well a numerical weather prediction model handles certain circumstances as opposed to others. And the same is true of hydrological models. Maybe storm direction or your parameterization could work better in certain circumstances and not as well in others. And we tend to develop probabilistic techniques that kind of lump all that together and represent average conditions, which we probably never really experience, but work in the general sense. So this is another challenge for us. So the last one that I want to talk about in a little bit more detail is really relates to communication. So how do we provide this uncertainty information to consumers of that information that is that's useful? I think we're pretty good at generating it. We're less good at communicating it in terms that they understand and can apply to their particular actions. And it's quite a diverse set of consumers. If you think about it, they vary in education and training. We need to provide context, validation, verification information, and we need to provide information that is compatible with their decision support tools, not necessarily ours. And so this quote is one that I made a long time ago. Some people are eager to misuse probabilistic information, while others don't want anything to do with risk, uncertainty, and probability. I think I was on a disaster survey from the '97 floods in Mississippi, and I think it was with the East Grand Forks and the city manager. I was telling him about a range of forecasts that the North Central RFC was doing, and he said, well, you know, we don't want a range of forecasts. If you don't tell us exactly what it is, you're just not doing your job. So, you know, there's some folks really want just a number. And, you know, like I said in the beginning, just a number is always wrong, right? So understanding the spread about that, the uncertainty is really important for us. So that's a challenge. So if we start to look at that a little bit differently and tease this apart, we have challenges related to communicating probability and uncertainty. The general public has some vague notions about what that means, mostly related to gambling, probably. And it's there's an education gap, and I think it's on us to help them with examples and applications that are meaningful to them. We need to better understand, you know, risk management, right? And I'll talk a little bit more about that. There's a desperate need for lots of forecast verification. If you want somebody to trust your information, you really need to develop the cases where you show how well it works or how well it doesn't work. We need to be honest about all of that. And finally, we'll talk a little bit more about the role and value of reforecasts and hindcasts, which I believe are critical to this effort associated with ensembles. So, you know, communicating probability uncertainty,